Hi guys, this is lesson. I'm writing this down so that you know what you should be writing in your notes. Lesson 7-3, and it is called Rational Exponents. Anytime you see the word rational, you see the word ratio, and that's going to mean that we're dealing with fractions. So what do you suppose happens if we have an exponent that's a fraction? So let's explore this just for a second. What if I have b to the 1/2? That's weird, huh? A 1/2 as an exponent. And let's say I have b to the 1/2 squared. Well, we know that that would equal b to the 1/2 times b to the 1/2, because we already know the rule that tells us that an exponent on an exponent means that we are going to apply this to the b to the 1/2. So that would mean that we would add our exponents, 1/2 and 1/2. And 1/2 plus 1/2 is 1. So b to the 1/2 is actually the same thing as the square root of b. Remember that the square root of something is looking for the number times itself that equals the thing. So that may be very confusing, but here is what we're going to talk about today. Whenever we have an exponent and we have a fraction, the exponent is a fraction. The top of the fraction is going to be the power, kind of like what we're used to, b squared or something like that. And the bottom of it is going to be the root. So let's explore that some more. Here is our first key concept. You're writing this down, key concept. B to the 1/2. For any number b to the 1/2 equals the square root of b. They're actually just two different ways of writing the same thing. So here's a couple examples. Make sure you write all of them. 16 to the 1/2 is the same thing as saying, what is the square root of 16? Which is the same thing as 4. Or if I had something like 38 to the 1/2, that's the same thing as saying the square root of 38, which doesn't simplify nicely, so we'll just leave it the way it is. All right, so a couple examples. Those are good examples, but here's another example. What if I have 25 to the 1/2 power? That's just the same thing as the square root of 25, and since 5 times 5 is 25, the square root of 25 is 5. Another one, the square root of 18. If I wanted to write it as with an exponent instead of a square root sign, I would say 18 to the 1/2. So that's not too bad. We can go back and forth between 1/2 and the square root sign. But what if, here's the next key concept, nth root. So there are other things besides square roots. There are cube roots and fourth roots and fifth roots and things like that. So we are going to say that if we have a to the n, and if a to the n equals something, let's say b, then the nth root of b is going to equal a. Or here's an example that's maybe a little more tangible. 2 to the 4th equals 16, right? Because 2 times 2 times 2 times 2 is 16. 2 is a fourth root of 16. So we could say the fourth root of 16, that's how we write it. We put a little number in there, equals 2. So whenever we have a root of something that's not a square root, we can have any root, but it just we'll be trying to find what number multiplied that number of times will give us the number that's underneath here. Here's a couple examples of some roots other than square roots. The third root of 27 equals the third root of 3 times 3 is 9, and 9 times 3 is 27. So I could break it down like that so you could see that 3 times 3 times 3 gives me 27. So the third root of 27 is 3, because 3 times itself, 3 times, gives me 27. Here's another one. What if I have the fifth root of 32? Well, what number multiplied by itself 5 times will give me 32? Let me give you a hint. We often work with 2s and 3s and maybe 4s or 5s, but because they get pretty big, often the examples don't deal with other numbers, so be looking for those numbers. 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. There are 5 2's there. 1, 2, 3, 4, 5. So the fifth root of 32 is 2. What do you think the third root of 64 is? Well, what number multiplied times itself? We could try it. 2 times 2 times 2 isn't going to be big enough. 3 times 3 times 3 isn't even big enough. How about 4 times 4, which is 16, times 4, which is 64? So the third root of 64 is 4. Or this one actually is not so bad. The fourth root of 10,000. Notice that there are 4 zeros, because that means that 10 times 10 times 10 times 10 would give me 10,000. So there are 4 10s, and the fourth root of 10,000 is just 10. All right, so let's move this on to a little bit more a connected concept. Key concept. You've written key concept 3 times in your notes today. B to the 1 over n. So instead of just b to the 1/2, we can have any number. B to the 1 over n is the same thing as the nth root of b. Notice that there's a 1 on the top here. We can have other numbers, but right now we're just dealing with a 1 because the bottom of the fraction is always the root, okay? So if I have something like, let's put a number to this, 8 to the 1/3, that just means I am talking about the third root of 8. And the third root of 8 is 2, because 2 times 2 is 4, times 2 is 8. We could have said the third root of 2 times 2 times 2, and we're looking for 3 numbers exactly the same. All right, sometimes we see some problems like, let's look at this one, 125 to the 1/3 power. Well, what is that the same as? The third root of 125. Would be the same as 5 times 5 is 25, times 5 is 125, so that would be 5. You might see something as awful looking as this, and you might have to explore this in a calculator. Really, calculators can do fourth roots just fine, so we're really just kind of challenging ourselves here. This is the same thing as the fourth root of 1296, and so you could probably guess that it's going to be something a little bit bigger. This happens to be 6. So when I get to those like that, then I'm generally leaning on a calculator a little bit. Okay, so let's move on to another key concept that's just one more step further. Key concept. How many times have you written that now? A bunch. B to the m over n. Okay, when I've already told you this, but let's sum it up. If I have b to the m over n, that is going to equal the nth root of b to the m. So the top of the fraction, if I'm writing it, you are too, equals the power. I'm going to call it the power even though I don't think that's actually technically correct to say that. That's the exponent, right? The bottom of the fraction is the root. Okay, so here's an example. What if I had 8 to the 2/3 power? This is the same thing as the third root of 8 squared. All right, the third root of 8 squared, well, we could also call it this, the third root of 8 squared. And those two things are going to be the same. But one is easier to do than the other. It is easier to figure out the third root of 8 than it is to figure out and then do the squared part than it is to square the 8 and then do the third root. So let's do the third root of 8, which would be 2, right? 2 times 2 times 2. And then we're going to square it and get 4. So figure if you have to do this by hand, figure the root first, usually. Although order of operations actually doesn't matter here. Figure the root first, then square. Or let's say that better. Then the power, or the exponent. All right, so here's some more examples of this. 64 to the 2/3 power. And you should be stopping this video so that you can try these on your own and then let me fill it in where you get confused. I want to do the third root first. This is going to be the third root of 64, and then we're going to square it. The root part is just easier. The third root of 64 isn't 8 times 8. It could be 4 times 4 times 4. It is, right? I think we've actually done that one before. 4 times 4 times 4 is 64. So the third root of 64 is 4, and then we still need to square it. Well, 4 squared is 16. That's kind of cool. All right, what if I had to do 36 to the 3/2? Okay, I'm going to do the square root. We don't usually write in, excuse me, we don't usually write in the 2 when we do a square root because that's just the same things we were doing, but then we're going to cube it. So the first thing we want to do is the square root of 36. That's 6. And then we're going to do 6 to the 3rd power. 6 times 6 is 36. And 36 times 6 is 216. Cool. All right. So sometimes we can take a little shortcut if we have an exponential equation. Let me show you another key concept. Power property of equality. And the power property of equality tells me that if I have something like this, b to the x equals b to the y, then x is going to equal y. And this comes in handy if we put numbers to this. 5 to the x equals 5 to the 3rd power. Now, notice that we had b and we had b. And we have 5 and we have 5. If the bases match, then we can just skip to the tops and say x equals 3. Well, that would be true, right? 5 to the 3rd equals 5 to the 3rd. So let's do one where it's not quite so simple. 6 to the x equals 216. Well, can we write 216 as a 6 to the something? 6 to the x equals 6 to the, Well, we actually saw that one just a few problems ago. 6 to the 3rd is the same. 6 times 6 is 36, times 6 is 216. We actually saw that in an example. So once the bases are the same, I can skip to the tops and say x equals 3. So now we need to kind of go back because, yeah, that's actually what we want to know. X equals 3. because 6 to the third is going to equal 216. Let's try something that has a little more obvious something that we want to solve for. How about this? All right, can we make the bases all 5? Sure we can. 5 squared is the same thing as 25. We still have to keep it to the x minus 1 power. Aha. Does that make sense? 5 squared is 25, and 25 to the x minus 1 equals 5. And this is just going to have a 1, right? So let's make this just a little easier to work with. Remember, we multiply exponents like that, so we're actually using the distributive property, and we're going to call this 2x minus 2. So this is 5 to the 2x minus 2 equals 5 to the 1. Cool. Bases are the same. Let's skip to the tops. 2x minus 2 equals 1. Well, that's not so bad. Plus 2, so I get 2x equals 3, and then I'm going to divide by 2, and I get x equals 3/2. So I could have had 25 to the x minus 1, or 25 to the 3/2 minus 1 equals 5. All right. Let's say let's do another one that looks like something we might want to solve. 2x plus 3 equals 144. Can we get these bases the same? Yes, we can. 2x plus 3 equals 12 squared. Bases are the same. Skip to the tops. 2x plus 2 equals 2. Well, that's interesting. Minus 2. 2x equals 0. Oh, this is a 3. No wonder. We don't have a 0. No. Okay. This is a 3. 3 minus 3. 2x equals negative 1. Divide by 2, x equals a negative 1/2. And we need to be able to evaluate and rewrite expressions involving rational exponents. That's just being able to say something like this: b to the 1/2 equals the square root of b. And we need to solve equations involving expressions with rational exponents. So if the bases are exactly the same, then we can just make the exponents equal each other. So hopefully that's helpful, and we'll see you next time.